Okay, I'm having some kind of issue with my webcam tonight, so you're not going to be able to see me during this video, but it shouldn't make that much of a difference. What we're going to be talking about today is balancing chemical equations. So before we start talking about balancing them, I just wanted to go over in real general terms what a chemical equation is. So the basic idea is that it's a description of a chemical reaction or a chemical change. It tells you what's changing with these compounds and how the bonds between them are changing from one side to the other. So there's a couple of different terms here that we've talked about before. We're just going to go over them again real quick. Everything on the left side of the equation is what's called a reactant. It's what your starting material is. Everything on the right side after the arrow is a product. It's what is made by the reaction. Okay, and then the arrow in the middle is just called the reaction symbol. And all it does is tell you which direction this reaction is going. Okay, a couple other terms that I've definitely thrown around before, but maybe we haven't defined fully, are subscripts and coefficients. So subscripts tell you how many atoms of an element are in one molecule, and they are the little small numbers that are inside the formula for the molecule. So in H2O, the subscripts would be this 2 here. That's what we're looking at. And that tells us that there are 2 atoms of hydrogen in this molecule. If there is no subscript, it just means that there's only 1. So H2O has 2 hydrogens and 1 oxygen. Okay, the other types of number you'll be seeing is what's called a coefficient, and those are the numbers that come out front before the formula for whatever molecule we're talking about. And that tells you how many molecules there are of that entire compound. So if your equation says 3 H2Os, that means there are 3 whole water molecules. Right, and this will come into play later on when we start talking about actually balancing things. Okay, one other major concept that we need to touch on is in physics and chemistry and science in general, there's such a thing as the law of conservation of mass. And what this means is that in any chemical reaction, no matter what, we can't make matter out of nothing, and we can't totally destroy matter either. So we're never going to end up with more mass or less mass overall on one side of the reaction than the other. And that applies to the number of atoms as well. So however many atoms of a certain type you have in your reactants, you have to have that same exact number of that type of atom in your product as well. Otherwise, your reaction is not balanced and it can't actually work in the real world, right? So an example of an unbalanced equation, if we're looking here, this is the combustion of methane equation that we saw in lab with the bubbles the other day, or that you saw in your homework as well. So if we just look at it right here, we're saying we've got 1 methane, 1 oxygen, yielding 1 CO2 and 1 H2O, right? So this guy here is the methane, and this guy is your O2, and we've got CO2 right here and H2O. If we were to look at the individual atoms of each element in this reaction, we would have 1 carbon atom on the left on our reactants, that's this big gray guy in the middle, 4 hydrogens, all these part of this CH4 molecule, and 2 oxygens in our O2. So that's what we have on the reactant side. On the product side, we've got 1 carbon, so that's fine. The same on either side, 1 carbon and 1 carbon. But over here, we only have 2 hydrogens, and we have 1, 2, 3 of these red oxygen atoms. So if we leave our reaction like this, somehow we're saying we destroyed 2 of those hydrogen atoms that were over here. They're just gone now. And we created from nowhere an extra oxygen. And that's just not possible, right? That breaks the law of conservation of mass. We can't do that. So what we can do to balance this out is to change the coefficients in front of some of these chemicals and change how many of these we have to start with, and that can help us balance out our reaction in the long run. So if we looked back at this and said instead of just having 1 of each of them like we do here, what if we had 2 oxygens and 2 waters? So then if we go through and we count everything up, we have 1 carbon, the gray one still, and that's still the same over here, so we're good with that. We've got 4 hydrogens. If we look over here, we've got 1, 2, 3, 4 hydrogens again, so those seem to match up. And 4 oxygens total. 1, 2, 3, 4 red guys here, and 1, 2, 3, 4 red guys over here, right? So now they all match up, and we did that just by changing these coefficients. Our law of conservation of mass is true. We didn't create any atoms or destroy any atoms, and we have the same number on either side of our equation. So that's what we're looking to do. All right. So there's a couple of rules and tips that you have to follow when you're balancing these equations. The first rule that always has to be true, just like we just talked about, is that matter cannot be created or destroyed. Law of conservation of mass. You have to have the same number of every type of atom on the left side as you do on the right side. Okay, the second rule is that while we are trying to balance these, the subscripts cannot be added, removed, changed, switched around, whatever. The subscripts in the formulas themselves have to stay exactly the same. All right, so if we were to look at this and say, if we just made this O3 instead of O2, that would solve our oxygen problem, balancing out, right? We have 3 on either side, but that is something we cannot do. The only things we can change are the numbers out in front, the coefficients. And that's rule 3, right? You can only change coefficients. The fourth rule is that coefficients can only go in front of a chemical formula, never in the middle. So what that means is we can't decide that we want to put a coefficient right here between, C and H, and just say, C and then 4 H4s to get more H's. We can't do that. If we're going to change the coefficient, it has to apply to the entire molecule. Okay. A couple extra tips that might save you a little bit of time that you can refer back to these. I always think it's easier to balance out the big molecules first, and then if you have any elements floating around on their own, do those last, and you can just use them as kind of the makeup at the end, right? You don't want to try and balance the small elements first, and then you change a big formula somewhere else, and it messes that up, and you have to go back and change it again, and back and forth. It's always easiest to do the biggest formulas first. Okay. If in a question you see the same polyatomic ion appear on both sides of the equation, so let's say you've got iron sulfate on one side of the equation and lead sulfate on the other, so FeSO4 and PbSO4. That SO4, the sulfate, you can just treat as one big chunk. You don't have to break it down into sulfurs and oxygens. You can just treat it as sulfates. Excuse me. All right, and then the third tip is there's not really one set in stone way to do every problem. Some you might have to trial and error your way through, use a little bit of problem solving and creativity, and it can get a little bit frustrating, but stick with it. Give it a couple attempts before you give up, and most of the time you'll be able to figure out something that works. Okay, so we'll do a couple examples here, and then I will show you guys 1 or 2 of the homework problems as well. But the first example, this one's nice and simple, right? The easiest way that I've found to do these is to make a kind of table like this if you don't want to draw out the elements, which you can do if you're a visual learner. But me personally, I think this table is quicker. So what I like to do is start off by just assuming there's one of everything and make a table like this. So if we assume there's one of each of these molecules and we're looking at our reactants, we would have N2 means we have 2 nitrogens, and H2 means we have 2 hydrogens. Okay, so that's on the left side of the arrow. On the right side of the arrow, in our products, we've got NH3. So that's 1 nitrogen and 3 hydrogens. Okay? So we've got to do something here to get this to balance out, right? Because they don't match up. We don't have the same number of everything on either side. So we got to do something to fix that. The easiest way, I think, to start this is by saying if we have 1 nitrogen over here on the product side and 2 over here on the reactant side, we can put in a 2 right here in order to fix that problem. All right, so when we do that, we have to multiply everything inside of this molecule that the 2 is applying to by the coefficient. So what that does is it gives us 2 nitrogens, but it also gives us 2 times the 3 hydrogens, 6 hydrogens there. All right, so by doing that, we made our nitrogens match up, but now our hydrogens do not. So we got to do one more step. We can come over here and say, what coefficient can we put here in front of the H2 to make it balance out with the 6 hydrogens that we have on the other side? If we put in that 3 right there, 3 times 2 is equal to 6, and now everything is balanced out. You have 2 nitrogens on the left and 2 nitrogens on the right. You have 6 hydrogens on the left and 6 hydrogens on the right. Everything is balanced. Our law of conservation of mass is satisfied, and the only thing we've changed is these coefficients. So we're good to go. All right. Let's look at this one here. This one we have 3 different elements that we're worried about. So just like we did last time, we're going to split them up into the individual elements, and we are going to look at how many of them we have on the reactant side and how many of them we have on the product side. So over here on the reactant side, we have 1 potassium, so 1 K. We have 1 Cl, and we have 3 oxygens. So we filled all those in. On the product side, on the right side, we have 1 potassium, 1 chlorine, and 2 oxygens. All right, so looking at this, our potassiums match up, our chlorines match up. So to start off with, the only thing we're really worried about here is our oxygens. We've got 3 of them on one side and 2 of them on the other. All right, and we've got to find a way to make those balance out. So we can't come in here and just change this to a 3 because we're not allowed to change our subscripts, right? The only things we can change are coefficients. So we've got to find basically the smallest common factor between 3 and 2, right? And that would be 6. So in order to get these to match up, we need to set them both equal to 6. So we'll come in here and we'll plop a 2 in front of our KClO3. And when we do that, it changes our oxygen to a 6, but it also changes this K and the Cl to 2s because it affects the entire molecule. Right, so you gotta pay attention to that. All right, in order to balance that out with the Ks and the Cls, we need to put a 2 in front of this on the right side. That way these are both 2s. And then finally, we put a 3 here in front of the O2. 3 times 2 is 6, which is what we had decided we were aiming for earlier. And now this is a balanced chemical equation. You have the same number of each element on either side of your reaction. Okay, so that's what y'all are going to be doing. It takes a little bit of trial and error, a little bit of practice. But if you have any questions, let me know, and I will help you out with it. All right? Good luck.